Hello, and welcome. So I started off with this code project by developing the disparity image. I first looked at an OpenCV sample to get a feel how they would do that. I'm using Python just so that I can do the development more quickly than I would be able to do in C++. I kind of assume that converting it from Python to C++ is trivial. I programmed in C++ for many years, but I wanted to get down all of the syntax and understand exactly the OpenCV commands before I would tackle something like that. So the first problem I ran into was after I had calculated the disparity image, there were many pixels that did not have a valid value for disparity. And the reason for that is I actually split the RGB image into three separate planes, the red plane, the green plane, and the blue plane, and I calculated the disparity on each of those. And the disparity just wasn't returning enough values. I think it kind of expects to have a gray value. I do think you could probably take the approach I took with some tweaking and some modification and merge all those into a single image, but it was clear that the algorithm wasn't really developed with that in mind. So once I had converted to a grayscale image, I got at a reasonable disparity value. The next thing I did is I took the left and the right images and I calculated what the disparity values should be. So I looked at some things in the in the forefront of the image and some things in the background, and I figured I should have a range of roughly 20 to 40 for the pixel values out. So I then examined the disparity image that came out of OpenCV, and the values were actually 16 times that. So then in order to get the correct value, I divided by 16. And then later on, I did find some other sample code, and that kind of confirmed that division. I didn't see anything in the documentation about the 16. That is kind of, before taking the code into production, I would certainly want to understand that and kind of have a better feel for a couple of the other parameters. I did get a good feel for many of the parameters in stereo.compute, but I wouldn't say I understand them all. I do have a general understanding of the principles they're using to calculate the disparity image. I don't know all of the specifics of this particular algorithm. Anyway, so once the floating point image was computed, the challenge became to convert it to an unsigned integer image, which is what was requested in the first part of the coding challenge. I first did kind of a rough order of magnitude pass and compared that against the ground truth that they had established in the link that you sent. And I came up with some reasonable values. Later on, I refined it and got the precise calculation for the slope and for the offset, and that brought it in even closer. And so there's very little difference between the ground truth and the, well, maybe not very little difference, but an expected amount of artifact between the ground truth and the calculated disparity image. So once I finished that, I looked on converting that image to a PLY file. That's a file I'm familiar with. I thought that would be a good way of convert to a PLY file, I can say that, and then read in the PLY file and render that into OpenGL. So I'm not a OpenGL guru. I've used it a few times. I've loaded in point clouds, I've created meshes, I've done some double buffering exercises. So I figured I'd find an example on the internet that was reasonably close to what you asked for in the second part. So I found something where someone was creating some random numbers, a random number generator that was a point cloud, and I said, well, that's close enough. So I modified the initialization of their structure using the PLY file that I had created, and kind of just closed the interface there and made sure that the colors were loaded in correctly and so on. So that's that portion of it. I also included, just so you have a good idea between of the difference between my code and what other people had developed, I included the original file. So I made a folder called original, and there you'll find the original cloud.py. I've modified that very little, only to kind of initialize the data. And the other three files, I borrowed some code from Stereo Match, but I really had to massage it quite a bit to bring it in so that I wasn't calling different functions that were doing the same thing between I'm sorry, the names of the files eluded me there for a second, between what was originally Stereo Match and what I had is called Find Disparity. So eventually I had two pieces of code, originally Stereo Match and then Find Disparity, which Find Disparity is what I started with. And then I kind of merged all the functions that were doing similar things into one program, just so that I didn't think it's very professional to have two pieces of code doing largely the same thing. So that said, I encourage you to look at the differences between the original code and the code that I developed. You'll see in the presentation, in the zip file that I sent you, there's a presentation.doc that includes some of this talk, although I've kind of ad-libbed considerably here, but you'll get the gist of it. And that also includes a couple items that I think that I left undone. I wanted to give you something that was complete and working. For instance, I skipped unit tests. I think that is a very valuable next step. There's a couple magic numbers in the code, not very many. I tried to eliminate as many of those as possible. And then I also think having a configuration file is kind of a good next step. So having gotten through the boring part of my speech, now I'll show you a couple of the images, and you can, should you be unable to execute my code, then you can see it on the laptop here. You can hit stop.